Welcome back. Apologize, I finished grading my 210 lecture, which I have two of them. So it's almost 200 exams, and I did the same thing with uploading, scanning and uploading, and I wish I maybe shouldn't have done that, but once you start something, you got to finish. So we'll see if I'll be able to keep that pace up. It was very time consuming. Did you all, with by returning the exams through the grade book, was that helpful for you or not helpful? Anyone not even look at there yet? So remember, you can go into the exam, you can see. I think it's important, especially on the open answer ones, where you take a look. Again, you do know, you get to see your, and then also just for, you know, sometimes I make mistakes. You got to be able to catch my mistakes. If you had the right answer, we got to make sure you get credit, and occasionally that happens. So that's why I do it. I am still, see, today I get done a little earlier. My goal will be to go in and to review your exams. I think that's how I was going to do it. I think I can do it fairly quickly, and give some partial credit on. I think there was either two or three of the questions that I.
Two multiple choice and one open-ended question.
Okay,
Partial credit.
very good. So I've got those. I'm going to do a quick review of those, revise your points. Once I do it, I'll put an announcement. If I did an announcement and you had one of the alternate versions that didn't get credited, send me an email. I'll do, just to make sure I don't miss something. Okay, so let's before we get into today's lecture, it's it's exponential growth and decay, which is not a new concept. It's what we've been working with, but it's going to be applications. So we'll look at three specific application or examples. That's what we'll work through today, and then we'll go from there. But let's kind of see. Let's see. Where's my weekly schedule for exam 2? So let's kind of see. Sometimes these things just come up on us, right? Where are we? So we're 3.5 exponential growth and decay. So this is actually the last of our algebra section. We don't do too much fanfare with it. We'll start on Thursday. We'll start into trigonometry, angles and radian measure, and I might have I've got a nice little activity. We might do it a little bit here. We'll see. And then we get into our trigonometry. We do have fall break, and that's why next week we won't be meeting on Tuesday, right? So we get we get a little bit of break, and then we'll only do one section, two more sections, and then our exam. So let's just start here, 1, 2, 3 weeks before our next exam, and when we get to our exam, we'll do the same thing, where Tuesday will be a review session where we can work through some of the exam review questions and such, and then we'll have the exam on Thursday and do it all over again. Okay, so and also within my 210 class, as you hand back exams and stuff, I know in here some of you did fine. You were happy with it. Some of you were not as happy with what you did on the exam. The department policy is not to allow any retakes, but I got thinking of it, the final exam, since it is comprehensive, look at that as a retake, because I will. I'll see how you did on the questions on the final exam that are sort of a subset from exam 1, and if you do better, I'll give you'll get better. So your exam 1 is just a sort of a minimum score. You can get it improved by learning and doing well on the final. So as long as, and so everyone has the potential to get an A in the class still. So don't go by the scores completely. Go by understanding and doing well, and that will happen. That can still happen. Okay. Don't let a poor performance over here because you didn't understand do it, because a lot of times we move forward and you start to understand what you didn't understand the first time. Okay. Where are we? Okay, so we're ready for our exponential growth and decay, which is not too much in here. Let me turn this off. No. Disconnect from the phone. Okay, so exponential growth and decay. For exponential functions, what we're using is, we sort of talked about this one in terms of the continuous interest problem we did just at the end of the last one, where the letters were a little different, but we had e to the RT, right? P, e to the RT. Basically, the same thing works. I just disconnected it. Oh, okay. Where whenever we have basically continuous change. When we apply it here, it's going to be primarily to radioactive decay, because that's a continuous process that's ongoing. We can also apply it to population growth, because that's sort of ongoing. People are dying and babies are being born on a continuous basis. So large populations, it's not, a census might only be done every 10 years, but population change is happening sort of on a continuous basis. So this is our mantra, or our key formula we're going to look at. We always have this A naught, whatever you want to call it, P naught, A naught. This is our starting value. And again, we choose some time and we say this is the starting place. So there's going to be a starting value, and then we multiply it. This is where the exponential growth or decay happens. There is some constant, so they're using the letter K instead of C, because C is hard to write, I guess. So K, and then it's multiplied by time. So the exponent is some constant. If that constant's above 1, what do you think is going to happen? Actually, no, it's a little different. If that constant is positive, then what happens to the exponent? As time goes forward, it's positive, and so we've seen when we get a positive, it's going to be increasing. If that constant is negative, what's going to happen? It's going to decrease, because that's so like e to the minus t, that's actually 1 over e to the t, so that's going to be a decreasing function. Okay, and we'll see that on the next slide. So if k is bigger than 0, positive, we get growth. So that's one type of situation. Again, often happens with populations. We can also have populations that are decreasing. And then when k, oops, I didn't get that slide in there. I guess I'll write it in here. For k less than 0, we get decay. We get the amount is decreasing over time. And that one is primarily for radioactive decay, and that's how they can figure out how old a mummy is. In fact, that's one of our questions, is by how much of a radioactive carbon is remaining, because at one given time, everything had the same amount. As you die as a dead thing, something's dead, then over time, that amount of that carbon reduces. Okay, so we'll see similar here's one with a population. The population of Caseville was this much in 2005. We told it's growing exponentially, and we'll assume it's continuous exponential, so we'll use that one that we're using. We've got a value that it increased to in some future year. Now, the full question's not there, but one of the things we want to be able to do is what would be the equation, what would be the function that would give us this. So we'll take sort of 2 looks at this. And basically, we can use technology because we've advanced to that. I'll show you how to do that with the TI-84, so you could use it on the test if you want. We'd also do it somewhat analytically, but it all starts with that equation that the value is going to be the starting value e to the kt. We're going to take our information, so we know in 2005 we had 469,300. How about if we call 2005 year 0? I mean, we could do that, right? Bless you. And then what would year 2017 be? Well, you take 2017 and you subtract 2005. So as far as years since 2005, this is going to be 12. 5 from 7 is 2. So that would be year 12. So these are the 2 points we have. And the benefit we have of calling 2005 0 is, what is this value, 469,300? Where are we going to see that in the formula? A naught. Good, good. So that's going to go right here because that's our starting value. We made it our starting value. Okay, we typically will do that. So this value right here is going to be 469,300. E is not a variable, it is a number. But then we have K and we have T and we have this number here. So, and again, one thing you could do is you could put in 0 for T and solve it. But again, if you've got the starting value, we just let that be A. How can we figure out what K is? Because K and T, well, we've got this point. What variable is this 12? It's a T variable. And then what does this number here? It's an A. It's an output. And then, so then we'll have an equation with everything here except for K. And now we just need to solve for K. K is the only variable left. We use our techniques we've been doing. So remember, one way to go is we could isolate the exponential. So how would we do that? Wish I had color. What's that? You will, but not yet because it's not isolated. So before we do the natural log, what do we do first? Yeah, so we divide both sides by this number here. So we get e to the 12k equals some value. I guess I'll just use 527. 450 divided by 469,300, and I come up with 1.12390. And I would suggest using 4 or 5 decimals. Actually, if I go to 5 decimals, that 0 gets rounded up to a 1. And I just found, 4 is pretty accurate, but 5 is, if you go 5 decimal places, because it's exponential, typically it's pretty helpful. Okay, so that's that number. Now take the natural log of both sides, right? So we're going to take the natural log 1.12391, natural log of e to the 12k, and when we take that natural log, what happens to the exponent? We can put it as multiplication in the front. So this is natural log of e. What's the natural log of e? 1. So this becomes, so what we get is we get the natural log 1.12391 equals 12k. So to solve for k, divide both sides by 12, right? So I guess this one will work. Just have to turn it sideways. So now I take the natural log. I do have natural log here. I get 0.1168, and then if I divide that by 12, I get that k equals 0.00973, 1, 2, 3, 4, 5, and going down 5 decimal places. Anyone get the same thing? Good. I always feel better because I've got this. I know I make mistakes a lot, so it's okay. So that's our k. What does that mean? Well, if you remember from exponential continuous growth that this constant is kind of like the percent change per year. So that means if we do over 2 decimal places, that's like a 0.9% per year change, right? It's slow, relatively slow. But what that gives us is that now we could actually find the value at any time by going 469, by using this formula. So if this was 2017, this is now 2023, how much of what would the population be projected to be now, right? We could do that. And they had some ape questions. In fact, this one I took from the notes, so you can see if you go into the notes, you'll see it worked out. I didn't look at their workout, so hopefully they got the same thing I did. They might have done it in a different fashion, we'll see, but this is one way to do it. And then if you want to find A of 2023, right, we have to subtract 2005 from that to figure out what year we're in, and looks like that will be year 18. So if we plug in 18, we should get our population now at some given time. Yes, sir.
After you use this equation and you already have it set to growth, is there any way to show if there were ever to be like a decline in population, or do you have to change it?
It would change, and that's so what we've got is we've got 2 points, and then you're exactly a good question. You're thinking that this is any analysis we do is that the population growth never changes. We know that that's not true. When you get to calculus, you get to look at what if the rate of change is changing, which does happen. Algebra we can't really do. It's kind of static analysis. We have to take 2 years. That's the average rate of change, really, what we're doing for this. And so we just keep using that average rate of change, but we know things change. And that's where calculus is going to be more of an exact tool. And so we'll leave that off till next semester, but good question. Excellent. Because I always thought of that, the real world, no, it's not always changing by 0.9. Except things like radioactive decay, that it's a natural process that doesn't speed up or slow down, possibly, right? Unless there's solar flares, who knows? Maybe they do. So, right. So we could calculate this. Again, we'd pull up a calculator. Let me. Well, I guess I'll use my calculator here. So that's E. I think I still have my. Yeah, because I'm going to want to go here anyway. So let's go to the. Oh, I must have closed it. I thought I had my TI calculator already TI-84 ready to go, but we'll go here because I'm going to show you how to use it. We'll actually just put in the 2 points. We'll ask it to do exponential regression. I think we've got a formula for that, and I think it'll work. Might not, but close this one out. Okay. So before I calculate what it is with 18, well, let's go ahead and do that. So I could just do 4,690,300 E raised to the 0.00. What was the number? It was 9. What were the other digits? 73. And then I'll put an X up there. Now, depending upon your calculator, you may need to put parentheses around this to make sure it's all up in the exponent. For this one, we don't have to, but I'll do it anyway. Let's see, second insert. And then what we can do is we can just go to the table instead of the graph, and then scroll down to 18. And it tells us that we should have a population of 559,130 in the year 2023. And again, we could test, do we have that? Oh, if we have more or we have less, then we've got to see, well, the rate of change is changing, right? But how could we use this to actually find the equation? Let's go second stat. So this is a stat, not second stat, just stat. So just hit the stat button. This is actually a statistics feature. Let me go over to calc. We do have exponential regression. Let me see. Of course, yeah, I don't have any data in there. So the first step is we have to edit. This is where we give the points to the calculator. Okay, so I'm going to enter. If you have numbers in there already, if you go to the top, if you go to clear and enter, notice I've cleared off the list. List 1, I'm going to go clear and enter. Practices in list 1, we'll put our X values, and list 2, we'll put our Y values. How many of you have done any kind of regression before? A few of you, maybe. Okay, so this is a great feature. Especially if you're doing anything with research, we can put our data in here. So we know in year 2005, which we called year 0, and then 2017, which we called year 12. So I put in the X's first. This was 4,609,300. And then this one was just want to make it a little smaller. There we go. That's what I want. And come on. Okay. And then 527,450. 527,450. So we've got our 2 values in there. We hit back to stat because now we're going to have the calculator calculate the equation for us. Hopefully we get the same values that we got when we did it sort of manually, right? So we're going to go over to calc. This is exponential regression. We hit enter. Our X values are in list 1, our Y values are list 2. You could change that if you needed to. We're going to have it calculate. and it gets 469,300. That's our starting value. And look at that. Oh, this doesn't do E. 1.09781,857. So what they're doing here is they're not using continuous change like we're doing. I don't think the TI calculator has regression, and maybe that's why this book they decided to do the ones with E, because they know you can't go to your calculator and just have it do the regression. But like I was mentioning, that was about a 0.9%, right? That's what this is as well. But this is periodic change on an annual basis. Okay. Okay. So let's go ahead and look at another example. And again, sometimes we want to say, is the change happening on an annual basis or is it happening continuously? Again, with large populations, continuous, it is continuously changing. Certainly carbon-14 is continuously decaying. It's every moment it's decaying. So in this case, we're going to get a decay rate. What we find with exponentials is on an increasing one, that the doubling time, the time for the population, say, to double, will remain constant. So if it takes 50 years to double, it'll take 50 years, it'll double again, and so forth and so forth. With decay, what we measure is the half-life. How long does it take for half of the stuff to be gone, or for us to only have half of it? That's what we call half-life. And whatever that is, that's consistent across the it's just consistent. So this is carbon-14 has a half-life of 5,730 years. Find an exponential function that models the amount of carbon-14 left after t years. So we've got to do a little bit of problem solving. I believe if you're in chemistry, you may have, there's a special formula they have that incorporates that half-life, and you just plug the half-life into the formula and you got it. We're going to start here with just the concept of half-life. So how much, we don't have much information, right? We know that we'll have half of whatever we started with after 5,730 years. So how do we use this equation? What do we put? What do we put where? They don't tell us how much we start with, did they? So what do we get to do? We get to make it up. Yeah. So you could put how much you want to start with? Or we could say we have 100% or just 1. We could call it one unit. We have e to the k. And then if we know what's going to happen in 5,730 years, we're only going to have half. Right? What's half of 1? 0.5 or 1/2 if you want to write it as a fraction. I like decimals. Good. So this is a setup we could do. Now you could have said you started with 2 and then you end with 1. Could have said 10,000 is what I started with, 5,000 is what I ended. So you could do that. The thing is you would do this. You would do a division first, and you'd always end up with it's always equal to 1/2 or 0.5. So it doesn't matter what you choose for what you start with, as long as you end up with half, you're going to have the same formula, which is 0.5. 1 times this is the same, e to the k, 5,730. Okay, does that make sense? Now what do we need to do? Natural log of both sides. You could do this with the log dance, does the same thing, but we'll take the natural log of each side This is just staying the natural log of 0.5. So you'll see whenever we're doing half-life, this is what they did in chemistry, is that's a particular value. So they embed that in the formula. You plug in your half-life. And then this is going to come down, right? So we get that 5,730 K. I just moved the K to the back side because that's a little bit more, is equal to the natural log of 0.5. Solve for K. What do we do? Divide by 5,730. And this is the formula, again, that in chemistry that they would just use, that it's going to be the natural log of a half or the natural log of 0.5. And just clear that out. So natural log of 0.5. Where's my natural log? So I think on this one I have to enter 0.5 and then natural log. There it is. I get negative 0.69314. You divide that by 5,730 years, and I come up with that K is equal to negative 0.00012. And then a 0.9, but 1, 2, 3, 4, 5. So 5 places, maybe you want to go 6, but there's a 0 after that. Then there's a 9, so I could round it up to 1. Just depends on how accurate you want to be. I'll put a 1 more, so 6. Again, more decimal places, more accuracy. But notice this is a very slow process. It's less than so we move that decimal, it's less than 0.01% per year. So slow, but after 5,700 years, we have half of it left. So what's our formula? Well, the ending value depends upon what the starting value is. And again, they have to give us that e to the minus 0.000121. T. Got to remember that. So this is one where we just really found the constant. And then if we were given an amount, we could plug that in and figure out how much is going to be left in so many years and all that kind of stuff. But and that's what they would do. They solve this. They figure what they started with, how much is left. Then you can use this to find how many years has passed from whenever the original was to now. And that's what we're going to do on the next one. But again, we can find that constant that way. So you see, it's just a matter of setting things up. And this one, the hardest part is part of it we had to know half-life means that if we start with 1, we're going to end with 0.5. Okay, we could use that as our standard. Okay, now we're going to use that, so we'll probably use it here. We've got carbon 14. We just figured out what that means. We've got a formula for carbon 14, right? So a mummy was discovered that had 85% of its original carbon 14. So a lot of times we'll start with this and it's got 85%, we'll say it started with 100. So if it started with 100, it's got 85 grams, whatever units you want to use. Use the exponential decay model we found in example 2 to estimate the age of the mummy. Okay, so 85% is left. So we step back, we're going to take this. What we're going to do is for the mummy, we plug in 100 here, 85 there, and then we can solve for t. Okay. Remember that constant, I've got that here. So mummy has 85%, we'll call it 85 grams of carbon 14, started with 100. This is our 0.00021. I'm going to go that far just to be as accurate as I can. And then there's going to be a t here. We're going to solve for that time. mummies. Anyone got a guess how old the mummy is?
3,600 years.
Well, here, if it was 5,760 years, how much of its carbon-14 would be left? Half of it. So it's younger than that. It's not 5,000, it's younger than 5,000. So we can kind of see that. It's got 85%, so it means it's lost 15%, not 50%. Maybe 2,000 years, maybe 3,000. I don't know. We'll figure it out. But you can see how you can kind of, knowing what the half-life is, we know it's less than one half-life. So, okay, let's go ahead and solve. We divide both sides by 100. So again, you could have just done 0.85 because you would have known, okay, start with 1, end with 0.85. That's what we're going to get here. 0.85 equals E minus 0.000121 T. How do we solve an exponential? Natural log of both sides. You see how this, in this you're going to be using natural logs of both sides fairly regularly. In fact, I've seen students that you do so many of these, you look at the problem and you go, it's natural log of this divided by natural log of that, because that's usually, or something like that, right? So natural log of 0.85 over here, this exponent comes down in front. Natural log of E is 1, so that goes away. We have natural log of 0.85. And then we just need to divide by this number, negative 0.000121. So T is going to be equal to natural log of 0.85 divided by 0.000121. Natural log of 0.85 is actually also a negative number, so a negative divided by a negative, you'll see our answer is going to be positive, which means the mummy is not negative years old. Natural log of 0.85, I get negative 0.162518. And again, I just leave all those decimals in there. I go ahead and divide by negative 0.000121. That's not right. Let's see. Let's see. Let me try this again. Natural logs. Clear. 0.85 natural log divided by 0.000121. And I'm going to ignore the negative. I come up with at the time, it's a pretty young mummy, 1,343 years. Is that what? Yes.
I was gonna say, since we know what 50% of the sample is from the previous problem, can we divide by by 35% on the previous answer to get that answer? Since you extended back up to 85%.
I don't think that'll work because exponentials, if it was linear, it might work. It's a continuous process. So it also might get close because that's sort of thinking, when we use the percentages, that's sort of thinking periodic change, like annual change. And it'll be close, but not exact. Yeah. And then again, see, I was trying to get you to think of that, but it's not that half of the half-life is that, because exponential processes occur not linearly. So, yeah. So the mummy is 1,343 years old. Which again is a pretty young mummy. I think some of those went in the pyramids. Anyone know how old those pyramids are? Maybe go watch Nova or something, or look it up after.
But we know they are at least more than 2,000 years old because like we are in
Right.
Definitely before Christ.
Yes. So those were definitely there. And again, they would
Yeah,
do this.
sometime.
Of course, they don't tell us where this mummy was found, and there's other places in the world besides Egypt that mummies were that humans were mummified. Um, that's the most famous place. Um, but that's pretty much what you're going to be needing to do is an application. So you've got half-life, you've got doubling time that you could use with population growth, but we're using this basic formula and working through those problems. So let's while we're here, let's go ahead and because we got about a half hour left, so I just want to look over the homework so that you don't get in. Oh, there's a problem that we didn't touch. What, what's that? 13. Okay, we'll take a look. Let's see. I need to. This is 3.5, correct? Exponential growth and decay modeling. 16 question. Let me just start from the beginning and kind of go through these. And then we'll take a look at 13. Yeah, so we see that same type of question for 1. Something, again, similar with looking at that same exponential growth function, seeing which ones are growing faster. So I think we're all okay. Here's question 7. We've got some two data points, again, to find the constant, kind of like what we did on the carbon 14. Let's go to 13. Okay, half-life of a certain tranquilizer in the bloodstream is 36 hours. So take our medicine, 36 hours, half the medicine is still in our system, half has gone out. How long will it take for the drug to decay to 93% of the original dosage? So certainly less than 36 hours, right? Again, we couldn't say it's going to be 7% of 36 hours because it's not a linear process. But to do this, let's go ahead and take this example. Okay, so we've got this. So what we know is it has a half-life of 36 hours. So what's going to happen in 36 hours? We'll have half. How much did we take? It doesn't say, but we start with 1, right? 1%, 1 dosage, whatever you want to say. So we started with 1. After 36 hours, e to the k times 36 hours. Actually, I think I can. We're going to have 0.5. Okay, we don't really need that 1 there, right? Because 1 times anything is itself, so we'll save a step there. Take the natural log of both sides. So we get the natural log of 0.5. Natural log of e is 1, so we end up with 36k. Divide both sides by 36. And then we get that our constant is natural log of 0.5 divided by 36.
Negative.
Good. It should be negative because it's decaying. Hopefully.
0.0192.
get negative 0.01925 1, 2, 3, 4, 5. 5 decimal places should be enough. I don't know how much accuracy they're going to want. Be careful. They say to round to 1 decimal place, but you don't want to do that during the calculations, right? We rounded this to 1 decimal place, it'd be 0.0. So no, we don't want to round at this place. But this is not our answer. So be careful. This is not what we put in. They want to know how much time has gone by. So that only helps us with the equation. So we're going to have, what we do know is that now we have 93%. So I'm going to do 0.93. And we started with 100%. So the 1 is here. I'm leaving it off though. E to the negative 0.01925 t. We're going to solve for t, and this will tell us how much time has passed. That got us down to 93%. Did I get the 93% right? Yes, there we go. Okay, decayed to 93% of the original. So again, we'll take natural log of 0.93, natural log here. So we're going to get the natural log of 0.93, and notice we'll have negative 0.01925 t. So we're going to divide by negative 0.01925. That's what t is going to be. So let's see what we get. 3.76 hours. They want it rounded to 1 decimal place, so it should be 3.8. Let me see if I come up with the same thing. So 0.93 natural log divided by 0.01925. Yeah, 3.769. Rounding to 1 decimal place, I would say 3.8 hours. Yes.
Is the negative necessary for that, or is it just to show you that it's decaying?
It shows you it's decaying. It is necessary because when you do the natural log of 0.93, that actually is a negative number, and so then you're dividing by a negative number, which makes it positive. So, yeah. And yeah, so if this wasn't, otherwise without that, if you were to graph it, it's actually increasing. So after 3.8 hours, that's what's that. Is there a second part to the question? Let's just see if it works. Check the answer. It worked. You see what, were you doing something? Okay. Next question. Then it goes on to 14, something new. Okay. So just, yeah, there's, sometimes notice there's this calculation to get the constant, and sometimes you say, oh, I'm done, that's my answer. Well, no, that's just the first part of the question. Then I use that to get the other one. Be careful about that rounding. It might say 1 or 2 decimal places, but that doesn't mean why you're doing the calculation. Any number that's going to be in an exponent, make sure you have 5 decimal places of accuracy. Again, sometimes you'll get the right answer with 4, but I found that going with 5, you just get that much more accuracy. 6 usually doesn't help that much more. You get close enough with 5. Because again, when we round, the final answer, we will round to 1 or 2 decimal places, so those extra ones don't matter. But if you only round to 3 decimal places, you could be significantly off on your answer when you round it. Okay, so 5, just a general thing, 5 decimal places for anything in an exponent or a logarithm, and you'll be good and on track. But you see, basically, that's the one function formula that we're dealing with. We need to find that constant by having 2 values of time and going forward. Sometimes we're told about doubling time or half-life, and we just, okay, that means if I have 100%, then I have 0.5, or if I have 100%, I have 2, right? I doubled if I've got growth. So if you're growing, you'll get double. If you're decaying, you'll get half, right? If you're decaying, you can't get double the amount, right? You're only going to get half. Okay, so those are the two types of applications we have. Some practice with that, and I think there's like just 16 questions. So what I will do, I didn't have anything on the logistic. This is a different type of function, and we have 2 questions on it. Let's start class on Thursday with a brief discussion about logistics questions. 5, 10, 15, maybe 15 minutes. We'll do good at it. But they are nice because where logistics problems come in is they're exponential for a while and then they level off. So a lot of times population growth is like that because the resources won't let you keep growing exponentially forever. You run out of resources, then your population levels off. That's logistics functions will do that for us. So I want to spend a little bit of time on that, and we'll talk about those Thursday, and then we'll move into our trigonometry. Okay, so again, one of the best ways, if you need an extension or anything, contact me through email. I think in this class what I've done with all the stuff from the first exam is it allows continual that you can continue to submit. I think I've removed all the penalties. There was like a 20% penalty if it was beyond a certain date. I think I've got all those out. But if you have any issues, just let me know, because sometimes I take them out, but there's a save button I didn't click or something. But the goal is that you can keep going back and reworking things until you get a good understanding. And if anything's not available to you, let me know, and we'll get that worked out. Keep you moving forward. Try to make you successful. This will be recorded and posted, and we'll be good to go. Still have 15 minutes, so if you want to work on some homework, you're welcome to do that. If you got questions, we can address that. I've got one person that was going to stop by for some office hours. I'll talk with them, and then I've got to get to my office to go through some exams, because that's where I've got them all stored, and make sure everything's working out. All right. Thank you all. Hi.
I just think that this will you find the formula of life.